So one of the reasons the AP exam uses questions like these to test your understanding of derivatives is because it really forces you to use the rules and trust the rules separate from particular functions or particular algebraic tricks. And if you can do that, it's going to allow you to use those same tricks in other situations. So we're going to move on to talking about trig functions. And we're going to start with two proofs, and then you're just going to really be using derivative rules for some other things. A proof is where you kind of know the answer, but the trick is really that you're trying to figure out how to show that the answer has to be right. So in this case, we've kind of already known that the derivative of sine is cosine, but the way that we knew that was from looking at the graph using your graphing calculator, and that's not actually proof. That was kind of a guess. It's a really good guess, and the fact that your math teacher is telling you it's right maybe means that you're pretty convinced. But remember, being convinced yourself is different from having proof. It wouldn't work in a court of law just to say, well, I'm convinced the defendant is innocent. You'd have to prove it. So we're going to prove that the derivative of sine has to be cosine using the limit definition. Here's how you'd set up your work. So first of all, you start with the statement of what you're trying to prove. And then I'm going to use a bunch of algebraic tricks to work from this, and ultimately I should end up with this. If I do that, I will have proved what I said I'd prove. Well, the first thing that we know about a derivative is that, formally speaking, the way that you take the derivative is you evaluate the limit of the difference quotient. So to start the proof, we just write the difference quotient. And then, of course, f of x plus h really means plug x plus h into the sine function, which gives me the limit as h approaches 0 of sine of x plus h minus sine of x all over h. To write a great proof, after each line of work, you should provide a justification. How do we know that this equals this? In this case, the justification is that this is true by the definition of a derivative. I like to use these arrows pointing to the equal signs to kind of indicate that this reason is the reason why I wrote this step and this step. The next step, we're going to want to simplify this limit, and just notice that you can't plug h in directly because it would cause a 0 on the bottom of the fraction, which isn't allowed. But also notice that I can't just cross out h. It might be tempting for some people to cross out h here and here, but remember, this h is inside the sine function. There's no way to simplify that or pull that out. By the same token, you can't split this sine into sine of x plus sine of h. That's not how sine works. Some things work that way, but not this function. And so I'm kind of stuck for a moment. Now, the next thing I'm going to do actually is going to be to use a rule from trigonometry, which you may or may not have learned last year. It's called an angle sum identity. And it's a formula that allows me to rewrite sine of x plus h in another way, in a way that might be easier to simplify. Truth be told, I don't always remember this formula. I always remember that it exists. And when I know that it exists, I usually just look for it on Google. So that's what we're going to do. And this is a totally legitimate thing to do, obviously not on a test, but in general. If I Google angle sum identity, you'll come up to Wikipedia, and there'll be just a list of formulas. Wikipedia is accurate for math through fairly advanced math. So maybe it's a good idea to double check with somebody else when you do this, but in general, it's fine to trust Wikipedia. As you notice, I'm just scrolling down and I'm looking for something that says angle sum identity. And it looks like this is explaining them. I really just want the formula, and here we go. I'm in luck. So I've got two formulas, one for sine and one for cosine. And what these formulas are telling me is that if I'm trying to take sine of something plus something else, which I am, remember? Here we go, something plus something else. Well, in order to do that, all I really need to do is take sine of the first, multiply it by cosine of the second thing, and then add cosine of the first thing times sine of the second thing. Now, this is not a super easy formula to believe in. It's just something random. There is a way to prove it, and actually Wikipedia is showing you how. But for now, we're going to just trust it. It's something you learned last year. And we're going to apply this identity in order to replace sine. Here's what it would look like. I take out sine of x plus h, and in its place I put sine of x times cosine of h plus cosine of x times sine of h, and that's just from using that formula. Now, at initial glance, this might look like it got harder, but actually, there's going to be a sneaky way to rearrange this. And if you think back to the limit problem-solving seminars we did, we had this kind of goal, which was always to end up with one of a couple tricks. And one of the tricks we loved best with sine and cosine was that when your limit is approaching 0, we know that the sine of h over h is going to be 1. So I can imagine using these two terms in order to kind of deal with the problem with h. In order to do that, I'm going to group the last term and the first term together, and I'm going to take out a GCF, which would be sine of x. Here's what it would look like. Notice that I also justified my last step just by naming the angle sum identity. Okay, next step is just rearrange things. And I chose actually to split it up into two fractions at the same time. Take a moment to convince yourself that this really does equal what we had above. And if I had to explain how I got this, I would say it's the commutative property, which is just the property that allows you to rearrange terms. And I basically just switched the order of these two terms. And then fraction rules, which allow me to write a single fraction as the sum of two fractions that have the same denominator. Now, we're getting closer and closer to good news. And that's particularly because I can now rewrite each of these as products. Here's what it looks like. In this next step, I just took out a GCF. So right here, notice what would happen if I distributed this back in. You'd get exactly what we had here. And then I really just rewrote this very slightly. And believe it or not, we're basically at the answer. If you think about taking the limit as h approaches 0 of sine of x, well, there's no h here, so really the limit of sine of x is just sine of x because there's no h to plug in. And it turns out that the limit as h approaches 0 of cosine of h minus 1 over h is 0. This is something that we actually proved a while back in the limits section. I can just show you the proof really quickly. This is cosine of h minus 1 over h, which is that term right here. And we would use a conjugate, and it would turn into a sine because there's a Pythagorean identity. And then it would turn into 0 because sine of 0 is 0. Anyway, it turns into 1. We proved it a while back. So, sorry, it turns into 0. So this expression turns into 0. Cosine of x, well, there's no h there either, so that's going to be what it is. And the limit as h approaches 0 of sine of h over h is 1. So think about this limit. What we've got is really just sine of x times 0, which that cancels out, plus cosine of x times 1, which is really just cosine. And that means this whole limit turns out to just equal cosine of x. And if I zoom back out here, that's what we were trying to prove in the first place. We were trying to show that when you take the derivative of sine, and we did it the long way using the definition, eventually you end up with a cosine as your derivative. Hooray! And of course you end your proof with QED. We proved it. Done. Okay, this is a long process. Take a moment, look at each of these steps, and then I'm actually going to ask you to do one on your own. I want you to try cosine. The proof is going to look very, very similar, and you're going to want to use one of the angle identities. So you're trying to prove that the derivative of cosine equals negative sine of x. I'll let you look at my work, and actually I'll keep the trig identity up here because you're going to want to use the cosine identity. Again, you're trying to find the derivative of cosine. Go for it. Great. So here's what my proof looks like for cosine. And you can pause for a minute if you need to double check anything, maybe your negative symbols or something. I used that same cosine of h minus 1 over h assumption here, and I'm calling it a known limit, just like the other one. So here's the great news. Now that we know for sure what cosine and sine are, what their derivatives are, we can use these to find the rest of the trig functions, and we actually don't even have to go back to the limit definition to do it. Knowing cosine and sine and knowing your trig identities, which you better have memorized, we're going to be able to derive these 4 derivatives. I'm going to do tangent with you, and then you'll work out cosecant, secant, and cotangent. So we're trying to find the derivative of tangent. We know that there are a lot of ways to find the derivative. We could use the n-deriv function on your calculator. We could use the limit definition. We could use algebraic tricks. This is a beautiful moment where in derivatives we kind of circle back to that same idea that we encountered in limits, the idea of there isn't really a right or a wrong, it's a what can you try? What could you try for this? Exactly. The one thing we know about tangent is that tangent is the same thing as sine over cosine. Okay, so what if you wanted to take the derivative of sine divided by cosine? What would you do now? Yes, it's a quotient rule, and we'd set it up with u's and v's. As always, u has to be the top function and v has to be the bottom function. And then we find du and dv, and this is where we're going to use those derivatives that we just proved a second ago. The derivative of sine is cosine, and the derivative of cosine is negative sine. From there, we just set up the quotient rule, and I've highlighted the v functions in blue in case you're remembering the quotient rule using that kind of outside property. And then I just simplify. Cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared. And then this cool thing happens, which is cosine squared plus sine squared, that's a Pythagorean identity. Cosine squared plus sine squared just equals 1. So really what I have is 1 over cosine squared of x. And in some worlds, that would be a fine way to write the answer. There's actually a slightly kind of more succinct way to do it, which is if you think about it, this is really just 1 over cosine times 1 over cosine. And we have another name for 1 over cosine. 1 over cosine is the same thing as secant. So actually, this is secant times secant, or in other words, the derivative of tangent is secant squared of x. And that's it. That's the derivative. That's the most simplified answer. In fact, this is a derivative that you're going to have to memorize. Once you memorize it, this is a derivative that you can just use and assume, the same way we assume the derivative of sine is cosine. That's something to memorize. Take a second look at this process, see if there's anything confusing. Hopefully not. And you're going to follow the same process to figure out what the derivatives are for cosecant, secant, and cotangent. When you press play, I'm going to show you the answers. When you see my answers, make sure that you correct your own work, and then these 4 derivatives belong in cram. You need to memorize them. Go for it. Cosecant, secant, and cotangent. All right, here we go with the proofs. The derivative of cosecant is negative cosecant times cotangent. Pause if you need to look at the proof, otherwise I'm going to move on. The derivative of secant is secant times tangent. Notice that this one is positive, the other one was negative. The way I remember it is anytime you have a co, your derivative is negative, so the derivative of cosine is negative sine, and the derivative of cosecant is negative cosecant cotangent, but the other ones are all positive. The last one here, the derivative of cotangent, and it's negative cosecant squared of x. The last thing I'd like to do in this video is look at a couple very quick examples where we use these trig rules in application. For example, what if I wanted to find the derivative of 2 times sine of x minus tangent of x? Well, the truth is this is really easy because I know what the derivative of sine and tangent are. The difference rule tells me that all I have to do is find those derivatives and subtract them and multiply the first one by 2. That's the constant multiple rule. We'd end up with 2 times cosine of x minus secant squared, and that's it. That's it. Just your answer. How about if we wanted to take the derivative of cosine x over 1 plus sine of x? For this one, we would want a derivative of using the quotient rule. So I would choose my u and v, find their derivatives, and after I plug into the quotient rule, v du minus u dv over v squared, it's just a matter of really carefully simplifying. What I'm going to do is I'm first going to distribute this sign to both of these terms. And when I do that, I realize that I have a negative sine squared minus cosine squared, which is really kind of like negative 1 times sine squared plus cosine squared. So actually, these two terms together just make negative 1. And actually replacing that with negative 1 makes me realize that I can actually even cancel out a term, giving me this final answer. Take a look at the 3 for you, and then I'll quickly show you the answers. Here's 1 and 2, and 3.